Okay, so to really understand what's happening with the quantum eraser, we need to back up just a little bit, and I promise this will not be a boring physics lecture. Think of it more like we're detectives, and we need to understand the crime scene before we can understand the crime. So here's where it all starts. There's this foundational experiment in quantum physics called the double-slit experiment. It's been around since the 1800s, but scientists are still finding new ways it breaks our brains. Here's the setup. You have a light source, or you can use electrons, atoms, even molecules, doesn't matter. You fire particles at a barrier that has two thin slits cut into it. Behind the barrier, there's a screen that records where the particles land. Simple enough, right? Now, if particles behaved like little tiny bullets, you'd expect to see two bands on the back screen, one for each slit. Particles go through slit 1, make a mark. Particles go through slit 2, make a mark. Clean, predictable, boring. But that's not what happens. What you actually see is what's called an interference pattern, a series of alternating light and dark bands, like zebra stripes across the screen. And that pattern only happens when waves interfere with each other, like when you drop two rocks into a pond and the ripples overlap. Sometimes they add together, sometimes they cancel out. That's interference. So the particles, these tiny little things that we normally think of as things, are somehow behaving like waves. Each particle is apparently going through both slits simultaneously, interfering with itself and landing in a probability pattern that looks like waves. That alone is wild, but it gets weirder. What if we just watched? What if we put a detector at the slits to figure out which slit each particle actually goes through? Like, we're just trying to get information. We want to catch the particle in the act. So they set up the experiment again, this time with detectors at the slits. They fire the particles, and the interference pattern disappears. Just like that. Gone. Now you get the two bands, the boring bullet pattern. The moment you measure which slit a particle goes through, it stops behaving like a wave and starts behaving like a particle. It picks a side. It commits. The act of observation, of simply gaining information about the particle, collapses its wave-like behavior into one definite outcome. Now, scientists have a name for this. It's called wave function collapse. And the philosophical implications are staggering, because it suggests that particles don't have definite properties until they're observed. They exist in a superposition, a kind of blurry cloud of possibilities, until something or someone measures them. Reality, at the quantum level, seems to be participatory. It's not just sitting there waiting for you. It responds to being looked at. All right, so that's the foundation. Now here's where things get truly, genuinely strange. In 1982, physicist Marlin Scully had a thought experiment, and later, he and his colleagues actually ran versions of it in the lab. The question was this: what if we could erase the which path information after the particle has already been detected on the screen? Like, what if we could take back the measurement? Here's how a simplified version of the delayed choice quantum eraser works. Don't worry, I'll walk you through every piece. You fire particles. Let's use photons, particles of light, at the double-slit barrier. But before they hit the screen, you pass them through a special crystal that splits each photon into two entangled photons. We call them the signal photon and the idler photon. These two are quantum mechanically linked. They're a matched pair. The signal photon goes forward toward the main screen. The idler photon gets redirected toward a different detector setup. Now, here's the key. The idler photon carries information about which slit the original photon came from. So if you measure the idler photon, you can figure out the which path information, which slit the signal photon went through. And when you do that, when you allow yourself to know the path, the signal photons on the main screen show no interference pattern. Just like before, two bands, definite positions. But now, and this is the part that will mess you up, what if you set up the idler photon's path so that the which path information gets erased before it can be recorded? You route the idler photons through a setup where their path information is destroyed. It becomes fundamentally unknowable. When that happens, the interference pattern comes back. On the main screen, the signal photons, which already landed on the screen, retroactively form an interference pattern. That's the part that makes physicists lose sleep. Because the signal photons hit the detection screen before the idler photons even reach their detector. The sequence of events matters here. In time, the result on screen A appears to be influenced by a decision made after the fact, at screen B. This is the delayed choice quantum eraser, run by Yoon Ho Kim and colleagues in 1999, published in a peer-reviewed journal, replicated multiple times. This is not fringe science. This is textbook quantum mechanics. Okay, so deep breath. Let's talk about what's actually going on here, because there are a few ways physicists interpret this, and none of them are exactly comfortable. Interpretation 1. Retrocausality. This is the spicy one. Some physicists look at this experiment and say, maybe causality isn't as one-directional as we think. Maybe, in some sense, the future is influencing the past. The decision made about the idler photon, whether to preserve or erase the witch path information, seems to affect what the signal photon already did. If that's true, then the arrow of time at the quantum level is flexible. And that's a sentence I never thought I'd say without laughing. Interpretation 2. No communication, just correlation. Other physicists push back hard on the retrocausality framing. They'll point out, correctly, that you can't actually use this to send information backward in time. The interference pattern only becomes visible when you compare the signal photon results with the idler photon results, what's called a coincidence count. On its own, the signal photon screen looks random either way. You only see the pattern emerge when you sort the data by what happened to the idler. So no, you can't build a time machine. But the correlation across time is still deeply real and deeply weird. Interpretation 3. It's all about information. This is maybe the most philosophically satisfying framing. Some physicists, particularly those in the information theoretic school of quantum mechanics, would say this experiment is telling us something profound. Reality is fundamentally about information, not matter. What's real isn't the photon's position. It's what can be known about the photon's position. The universe doesn't just physically exist. It exists as a set of possible answers to possible questions. John Wheeler, one of the most important physicists of the 20th century, called this idea it from bit, the idea that physical existence itself emerges from information. That means, in some very real sense, the past isn't fully fixed. It's not sitting back there, solid and immovable. At the quantum level, the past exists in a kind of superposition until the information about it is either preserved or destroyed. The quantum eraser doesn't just erase witch path information. In a meaningful sense, it erases which version of the past existed. Now look, I know what some of you might be thinking. Cool experiment, but what does this have to do with my life? With the real world? And look, I'll be honest with you. On a practical day-to-day level, quantum effects don't typically show up at the scale of people and coffee cups in cars. The quantum world is tiny. Quantum superpositions get disrupted incredibly fast in warm, noisy environments like, the one you're sitting in right now. This phenomenon is called decoherence, and it's why we don't phase through walls or exist in multiple states at once. But here's the thing. Understanding the quantum eraser experiment matters because it forces us to confront some assumptions we didn't even know we were making. We assume that the past is fixed. We assume observation is passive. We assume that reality is something that just is, independent of anyone looking at it. The quantum eraser says, not so fast. Some researchers are now exploring whether quantum effects might play roles in biological processes, photosynthesis, bird navigation, and some are even speculating about human cognition, though that's still very early and controversial territory. The quantum world isn't as separate from the real world as we used to think. And more broadly, if you're someone who thinks about consciousness, about free will, about the nature of time, this experiment puts a crack in the wall of classical determinism. It opens up space for genuine uncertainty, genuine openness at the most fundamental level of reality. The universe, it turns out, is not a machine running a pre-written program. It's more like an improv performance that's writing itself as it goes, where the audience, the observers, are actually part of the show. So let's land this plane. The quantum eraser experiment tells us that 1. Particles exist in superpositions of possibilities until they're observed or their information is recorded. 2. When you erase which path information, even after the fact, interference patterns re-emerge, suggesting the particle's past behavior can be altered retroactively based on later information. 3. This doesn't mean we can send messages back in time, but it does mean that the relationship between cause, effect, time, and information is far stranger and more fluid than our everyday intuitions suggest. And 4. At its deepest level, reality might not be made of stuff at all. It might be made of information, of possible answers to possible questions, of observations waiting to happen. Wheeler put it beautifully when he said, "No phenomenon is a real phenomenon until it is an observed phenomenon." Now, whether that's exhilarating or terrifying probably says something about your personality. But either way, it's real. It's been tested. It's sitting right there at the foundation of modern physics. And I don't know about you, but I think there's something almost liberating about that. The idea that the universe isn't this cold, closed, predetermined thing grinding forward. That at some deep level, observation, awareness matters. That the act of paying attention is not just passive reception, but participation. You're not just watching the universe. You're, in some small but real way, part of how it decides what to be. If this kind of thing lights up your brain the way it lights up mine, stick around, because we've got so much more of this. We're going to be going deep on quantum entanglement, the many worlds interpretation, the holographic universe hypothesis, and a lot more experiments that sound like science fiction, but are sitting right there in peer-reviewed journals. Hit subscribe if you want to come along for that. And if you've got someone in your life who thinks they've got reality figured out, send them this video. Let's mess with their worldview a little, in the best possible way. I'll see you in the next one.